Welcome to this explainer. Today, we're decoding the absolute sheer chaos of a soccer counterattack. Football matches are so often won and lost in those frantic moments when nobody really has control. We're going to see exactly how artificial intelligence, specifically graph neural networks, is fundamentally changing the way we understand human strategy on the pitch. We aren't just talking about players running fast anymore. We're talking about the cold, calculated manipulation of space, time, and spatial geometry. All right, here's our roadmap for today. We'll be hitting 1. The 3-second countdown. 2. Beyond traditional soccer stats. 3. Enter graph neural networks. 4. The gender-specific data advantage. And finally, 5. The infinite search space.
Section 1. The 3-second countdown. Let's start right down on the pitch.
To build a perfect counterattack, you really have to know where it starts. It turns out, a staggering 70% of all goals scored from rapid counterattacks actually originate from turnovers won right in the middle third of the pitch. Why? Well, when you win the ball there, the opponent's defensive line just hasn't had time to drop deep yet. They're caught high, leaving vast acres of green grass behind them. At that moment, you are literally just 3 passes away from a high-quality shot on target. The exact millisecond that ball is recovered, a 3-second psychological countdown kicks off. You've got exactly 3 seconds to aggressively exploit the chaotic organization of the opponent before they recover their shape. Human instinct, right after defending intensely, is usually to take a breath and maybe make a slow, safe horizontal pass. But if you do that, the counterattack is dead. Your first thought absolutely must be aggressively vertical. This dynamic perfectly captures what coaches call rest offense. While your team is defending, the attackers aren't just standing around taking a break. They're actively positioning themselves in vacant corridors left by the opposing fullbacks. As soon as a midfielder intercepts the ball, those attackers are already hiding in plain sight, capitalizing on that split-second geometry to launch a devastating strike. Section 2, Beyond Traditional Soccer Stats. So how do we actually go about mathematically measuring these frantic transitions? For years, traditional analytics have relied heavily on metrics like expected goals, or XG, and ball progression tracking. And hey, these stats tell us a ton about individual brilliance. For instance, data over multiple Premier League seasons shows that a player like Granit Xhaka absolutely dominates ball progression during deep, fast attacks, thanks to his incredible long-range passing. Meanwhile, Kevin De Bruyne reigns supreme as the ultimate architect in the final third, leading the pack in expected goals and assists during these exact transitions. But here's the catch. As great as traditional metrics like XG are, they have a massive flaw. Without exhaustive locational tracking data, XG completely struggles to accurately account for off-ball defensive locations during these rapid, chaotic transitions. Think about it. When a team counters, defenders are scrambling back. They're completely out of shape. Traditional stats just look at the shot location, totally missing the geometric chaos that led up to it. Which brings us to the real solution. If you think about a standard coach's tactical whiteboard with all the arrows, zones, and basic player positioning, we need a way to bridge that gap into a stylized mathematical graph. To truly measure a counterattack, we have to look at the game exactly like a graph, a living, breathing web of spatial relationships. Section 3. Enter graph neural networks. It's time to decode the pitch. To decode this chaos, researchers at the U.S. Soccer Federation are leveraging state-of-the-art models built on tens of thousands of frames of spatiotemporal tracking data. They're doing this using graph neural networks, or GNNs. I find this absolutely fascinating. In our soccer explainer context, the players themselves become the nodes on the graph. Their spatial relationships, the distances and angles between every single player on the pitch and the ball, become the connecting edges. Every split-second frame of tracking data is fed right into this mathematical structure. And here is where the magic happens. By feeding raw tracking data into what are called crystal convoluters, which, fun fact, is a method originally built to predict the properties of crystals using atomic connections, these models completely bypass traditional image conversion. They directly learn the game state properties from the complex web of connections between players. This allows the AI to predict the exact probability of a successful counterattack in real time. Section 4. The gender-specific data advantage. When researchers split this massive dataset across MLS, NWSL, and international matches, they found something completely mind-blowing. They built separate models for men's data, women's data, and then a combined dataset. The data explicitly proves that gender-specific models actually outperform combined gender-ambiguous models. The women's model achieved an incredibly strong ROC-AUC score of 0.83, significantly beating out the blended model. What this tells us is that there are distinct, highly measurable tactical tendencies between the men's and women's games that a blended model simply dilutes. So, what's actually driving those predictions? Using a technique called permutation feature importance, which is basically a fancy way of saying they randomly shuffle specific data points to see what breaks the model, researchers can pinpoint exactly which player actions impact these algorithmic predictions the most. It turns out that a player's byline-to-byline speed, literally how fast they are sprinting straight up the pitch, and their direct angle to the goal are the absolute most crucial markers of success for both genders. But here is the real secret. Defensively disorganized features actually matter way more to the AI than the attacking features. A successful counterattack exists almost entirely because of the defensive team's structural collapse.
Section 5. The infinite search space. Let's look at how we can actively optimize player decision-making.
Imagine the technical staff having access to an interactive tool right there on the bench. They can pause a frame of tracking data, analyze a player's original run trajectory, and then ask the AI, hey, what if they ran just slightly differently? By modifying the run direction by just 15 to 30 degrees, the model instantly calculates the newly improved probability of success. When analyzing pitch control models, the optimization becomes so clear. By simply altering a left winger's run by 30 degrees outwards, moving away from a retreating defender and into a wider channel, the mathematical probability of scoring actively increases. You aren't just yelling at a player to run wide anymore. You're mathematically proving that doing so bumps the likelihood of a successful counterattack by a couple of vital percentage points. This brilliantly illustrates that exact optimization at work. In this specific scenario, finding the optimal angle for the player's trajectory causes the success prediction to jump from 76.2% to 77.6%. Running into a channel with more space directly translates to a measurable bump. And over the course of a 90-minute game, or a grueling 38-game season, those tiny fractional percentages, they're the literal difference between lifting a trophy and going home empty-handed. Next time you watch a game, realize you aren't just watching athletes run on grass. You are watching a living, breathing neural network calculating spatial geometry in real time. Which leaves us with one provocative final thought. If a graph neural network can uncover the literal mathematical perfection of a forward run, is the beautiful game still driven by raw human instinct? Or are we entering an era of pure algorithmic execution? Thanks for joining me on this explainer, and keep looking for the geometry in the chaos.